Okay, continuing, I wanted to show you an example or two that try to just illustrate what we just did in the theorem. Actually, I'll try to compute some of these idempotent transformations and so forth from the minimal polynomial. And I'll try to keep the example simple enough so that we can follow without too much work. Here's one, this block diagonal matrix, 3, 1, 0, 3, 2, 0, 0, 2. You can show has eigenvalues 3 and 2, all right? And if you look at the a minus 3i, you get this. So like a minus 3i squared is that. On the other hand, a minus 2i is this. If you take the product of this and that, you'll get 0, all right? And in fact, you can show that that's the smallest polynomial in A that will give you back 0. The minimal polynomial here is in fact, well, I should also mention we will soon learn that the minimal polynomial has to divide the characteristic polynomial. That's corollary 24.7 of section 24. We'll get there soon. So like if you know what the characteristic polynomial here is x minus 3 squared times x minus 2 squared. So basically there has to be an x minus 3 and there has to be an x minus 2 in the minimal polynomial. And then the question is just how many of them you need. Well, this one you happen to need 2 of the x minus 3's and just 1 of the x minus 2's for the minimal polynomial. That suffices. Minimal polynomial is cubic, whereas the characteristic polynomial here is quartic. They're not the same thing. But they're related. They have to share the same zeros, all right? That's helpful. Anyway, here we go. So just to reiterate, characteristic polynomial is that, whereas the minimal polynomial is that. Well, I a little bit later in these notes start saying that we reverse the order of the, I start looking at the characteristic polynomial as like xi minus a, because he does as well, Curtis does in the book. There's some choices you can make notationally here. I'll talk more about that as we go on, but anyway, there's the minimal polynomial. So in the notation of the proof, we have the first prime power is x minus 3, and e1 is 2, and then the second prime is x minus 2, and it's just to the power 1, right? So our first quotient, q1, would just be x minus 2, whereas q2 would be x minus 3. These are both prime. X minus 2 and x minus 3 are both prime. By the divisibility theory of polynomials over the real polynomials, we can find an a1 of x and a2 of x for which 1 is equal to like this plus that. All right. In other words, x1, x minus 2 times a1 plus x minus 3 times a2 gives me back 1 again. That leaves me with a question, of course, which is how on earth do you actually calculate these polynomials? Well, this feels kind of like partial fractions to me, and there is a method, a systematic method. I'm not going to try to show you that. I just show you some ad hoc methods, and I think the ad hoc methods I'll show you for now will suffice. If you really understand number theory, you probably could do something more sophisticated here, but you know what, this will work for us. So this one's kind of, it took me some time to figure this out, but after some calculation, I found that a1 of x is, there's like a page I'm not showing you here. It's not a terribly glorious page either. So let me just, after I tinkered and I was like, well, if I want this plus that to be back to 1, I need the cubic piece to cancel, or I need a quadratic piece to cancel, and well, I think I tried, I forget what I tried. Anyway, this is what I had to do in order to get the cubic pieces to cancel and so forth. Basically, I decided to look for an arbitrary quadratic here and an arbitrary linear over here, and then I just multiplied it out and wrote the equations that I got, and then did row reduction, and this solution popped out for me. Okay, like that's all I did. Just assume like an arbitrary quadratic and an arbitrary linear for my a1 and my a2, and I was able to solve for these. Now, once you find that, then we can kind of, I mean, that's, it's not obvious, okay, guys, how to find the a1 of x and a2 of x. I mean, that is, in some sense, a serious deficiency of what we're doing right now. But anyway, so once we have that, all right, that makes this my f1 and makes this is my f2, because that's like the, you know, the q1 a1, this is the q2 a2, all right? So allegedly, this is f1, that's f2, and then so e1 would be f1 of t, and e2 would be f2 of t, where t is the left multiplication by the matrix we're talking about here. And allegedly, the range of e1 is going to be the kernel of t minus 3 squared, and the range of e2, if we believe the proof, should be the kernel of t minus 2. All right, and you can try it out. It works. The matrix of e2 would be, you know, 1/2 of a times a minus 3 squared. I calculated those before. It's this and that. Well, that is that. So in fact, e2 is just 0, 0, 0i. It literally projects onto the second two factors. And, well, okay, so like if you feed e2 a, b, c, d, you get back out cd. All right. And you can easily check that the kernel of t minus 2 is in fact 0, 0, cd. So there it is, it's explicit right in front of us. The range of e2 is the kernel of the thing we divided by to construct e2, right? I mean, f2 was constructed by dividing out x minus 2. It's come back to us as the kernel of the image of the e2. It's cool. It's very cool. And then just to be lazy, I said, okay, well, to find the e1, and I'll be less lazy in the next one, I suppose, but to find e1, that's 1 minus e2, which is this minus that, which is the other projection onto the first two components, I, 0, 0, 0. And the kernel of t minus 3 squared would be the range of e1. It's the span of e1, e2. And that's also the case. You can go back to the original matrix and you can verify that, in fact, if you have if you have vectors where the first two components are anything and the second two components are 0, you get, in fact, you get eigen. Excuse me. Let me just go back. Sorry, no need to be lost here. Let me just not be dumb. If you go back here, the where was I? If we go back, well, if we go back to this one, right, a minus 3i squared, if you want to take a vector that makes this multiply on that to be 0, basically you can put anything you want in the first two components, right? When you multiply the first two columns being 0, we'll just go to 0. So, and on the other hand, if there's anything non-trivial in the third or the fourth components of the vector, it's not going to work to give you 0. So the kernel of this is exactly arbitrary things built from e1 and e2, which is what we came to over here from rather different means, right? Dividing this minimal polynomial by the other thing. Some kind of, so, you know, kernel t minus 3 squared was the range of e1, which is the span of e1, e2. All right. And you can also check that the e1 and e2 are commuting. We go on to my next example. Again, I would just refer you, I would, you know, caution you that the selection of the a1 and a2, I hid something there that wasn't terribly easy either. Okay. But I just wanted to exhibit the theorem for you. So here's another one. Here's a matrix which is a little bit uglier. It's got lots of numbers in it. Minus 2, minus 4, 2, minus 2, 1, 2, 4, 2, 5. The spectra, by the way, is a set of eigenvalues. Sometimes called spectrum. And Well, this is the same as the linear transformation txyz sends to this stuff, right? This is the matrix of that transformation for what it's worth. So you can calculate the determinant of a minus xi. You get this. That would be the characteristic polynomial of a, well, plus or minus the characteristic polynomial, depending on what we're reading. Fine. And then you can see you've got characteristic values, minus 5, 3, and 6. So for minus 5, you do the row reduction on this, you get that. All right, so I have trouble with my markers writing over the other things. Sorry about this. This is supposed to be the null space of a plus 5i. So the null space of a plus 5i has the form, it's basically a scalar multiple of minus 2, minus 1, 1. All right, so in other words, the basis for the kernel of t plus 5 is minus 2, 1, 1. Likewise, for 3, you can plug in a minus 3i, you get this matrix, you do row reduction, you get to that, and from that we can see that we get this basis for the null space. It's minus 2, 3, 1. So there's your kernel of t minus 3i. For 6, we get 1, 6, 16 after we do the row reduction. All right. So I thought it'd be helpful to see an example. I mean, I haven't showed you all the details, but you know, sometimes you really do have to do row reductions to find the eigenvectors, even when it's distinct and stuff. All right. Again, our real goal here, though, is to understand better understand the primary decomposition theorem and the 1 through ES's, right? In this case, the characteristic of the minimal polynomials have to be the same because we only have 3 distinct zeros to go around, and you need each one of them, right? And there's something called the Cayley-Hamilton theorem, by the way, which tells you if you plug in a into this, it's going to give you 0. So some texts insist m of x be monic, in which case we're off by a sign. Actually, Curtis insists that the characteristic polynomial is monic, so we're off by a sign. Oh well. Like I said, minimal polynomial, characteristic polynomial, plus or minus what any book says in another book is possible, all right? Beware of that. I'll try to be more systematic as I type up the notes. Oh my goodness, so many notes to type up. Okay, anyways, focus. All right, so P1 of x is this, P2 of x is that, P3 of x is that. These are my distinct prime factors in the minimal polynomial. So the first quotient is the product of the other two. The second quotient is the product of the other two. The middle, you know, and then the third quotient is the product of the first two, but not the third, right? You can multiply these things out. You get Q1 is minus x squared plus 9x minus 18. Q2 is that. Q3 is that, right? And then the proof of the theorem indicates that I can set EJ equal to QJT, and they will have ranges which reproduce the kernel of PJT. I think that's even true, but that's not quite what I did in the theorem. There's this other thing called A sub j that plays into the role here. It's kind of important. Let's just go on though. Let's just freewheeling, carefree, go on here, see what happens. Oh, this page had a problem. I had some deconstructing to do here. All right, just a second. Let me arrange this. Do some very old school editing here. All right. Not quite cutting and pasting, but pretty close. All right. So I say E1 tilde, which is my way of saying it's not really E1. Q1 of A is this. All right, so I plug in the numbers, and you multiply it, and guess what? Rank 1. Because this, and this are clearly just, you know, you're looking basically at 2, 1, minus 1. And this is 11 times this, and that's 14 times that. And oh, there's a 2 out here, so it's worse. All right, great. Anyway, there's E1 tilde. So the range of E1 tilde, in other words, is the column space of the matrix of E1 tilde. In fact, that's the span of 2, 1, minus 1. Well, hey, well, what do you know? That was almost exactly the kernel of t plus 5. right? So in other words, the range of the transformation we got from dividing out the x plus 5 factor in the minimal polynomial has given me back the, as its range, it's given me the kernel of everything that we divided by. Interesting. Cool. And you can try the same song and dance for E2 tilde and E3 tilde, and you can show that that will have kernel P2t and kernel P3t as, which is kernel T minus 3 and T minus 6. Here's one of those. So E2 tilde Q2A, which is the product of this and that, which is the product of this and that, which again is a rank 1 deal, because you got like 2, 3, 1, 6, 9, 3, 4. So this is all basically scalar multiples of the 2 minus 3, 1. That's 3 times that. That's 2 times that. Now there's this 2 out here, whatever. Anyway, the span, make sure you can see this. So the span of E2 tilde is the span of this 2 minus 3 minus 1, which is the kernel of T minus 3 we just found. Okay. And you can check that the product, I think it's more fun to look at this example than the previous one because it's not just block diagonals. I mean, here the fact that things commute to 0, it's like, it's a little bit more surprising than the last example. E1 tilde, E2 tilde is 4 times that, so that gives me 0, 0, 0, 0, 0, 0, 0, 0. And you can calculate E2 tilde, E1 tilde is also. So they're pairwise commuting to 0. And I was like, oh, this is awesome. This is easy, man. This is cool. I was pretty stoked about this. And then I calculated. I was like, all right, next I'm going to show it's idempotent. All right, keep in mind that the whole time I'm originally calculating this, I had neglected the fact that I was missing my A1 of x and my A2 of x and my A3 of x and the definitions of E1. All right, that's why there's tildes on these, because they're not the real E1, as you could clearly see here. See, because E1 tilde times E1 tilde is 4 times this, which is 4 times this, which is 44. There's a 44 that appears when you multiply this. I won't bore you with the details, but you get 176 E1 tilde. Well, that is like, kind of like, it gives me hope that it could be made idempotent, but clearly it is not scaled correctly, right? Like 176 times off. Oops. All right, so how do you fix that? Well, how do you fix that is the question, right? And so it's because my current E1 tilde is not constructed as we were instructed in the proof. EI is not equal to QIT, it's rather AIT QIT, all right? Where the AIs are the coefficients that are needed to make this linear combination be 1, right? There's a scaling that goes on in here, and this sets a normalization, right? So now this is the problem we face. We have to find polynomials A1, A2, A3, such that this linear combination is 1. Now this problem is more forgiving. In fact, we can just find scalars A, B, and C that do this. I'll show you the details even this time. The details which I hid from you in the last example. Yeah. All right. I mean, clearly there's a calculation here that I have not taught you in this course. I mean, I'm showing you an ad hoc method here, right? It's part of the reason that there's a take-home quiz on this and not an in-class test, is because I really have not given you the technology you need to solve these cleanly and efficiently and in any way fast. Certainly not. They're not impossible, but they require tinkering, and so at least in our current way of thinking. So what I do is I just say that's A, that's B, that's C. Wishful thinking, but it works. I mean, you can make a guess, right? And if it works, it works. If it doesn't, you try something the next up the chain. Maybe next I would. If this didn't work, I would have tried a linear, and a linear factor here, like ax plus b as cx plus d and ex plus f, and then I would have multiplied the whole thing out and like forced equating coefficients, and hopefully there's enough freedom in my guess, or if you're German, Ansatz, to make it work. Anyway, this works. So I collect together the x squared terms, I get minus a minus b minus c. I collect together the x terms, that gives me 9a, 9b. I mean, it should be b. And minus 2c, and then from the constants I get my minus 18 here, plus 30b here, and plus 15c, and those have to be respectively equal to 0, 0, and 1. So that's a job for row reduction. All right, so we do that, and you get -1 over. Well, you get other stuff. You get awful other stuff because you've neglected one sign up here, and you're an idiot. But no, that would be me. That's not you. So you just look at my answer. So -1 over 88, 1 over 24, -1 over 33 turn out to be A, B, and C respectively. Probably not fractions, I would have guessed real quick. As I said, if you make a sign error here, it hurts. It stings. Actually, it stings a lot. I did this a couple days ago. It still hurts me to look at this. Anyway, so the matrix of E1 is in fact 1/44th of that. All right, and now we can check. E1 squared is 1 over 44 times this, which then the 44 cancels the 44. I guess the presence of the 44 sort of suggested to me I should just divide by 44 if I'd been smarter. Oh well, we've established I'm not that smart, so let's go on. So 1 over 44, this gives me E1. And as you can see, idempotent. Woohoo! All right, so this finding the A1 through A3 is necessary to make it idempotent. On the flip side of things, if you don't care about the idempotent condition, I suppose there is something weaker you could do here where you still have pairwise commuting, but you just don't have the idempotent condition. There may be a weakened form here where we could avoid the calculation of A1, A2, and A3 and so forth, and yet still have a lot. I haven't thought about that too much yet, but it seems like it might be possible. In some sense, the idempotent is just to make the theorem, the proof of the theorem rather beautiful. I personally found it to be really quite stunning. The interplay between, to be able to find, I guess it's Bezout's theorem, or I don't know. Some people say Bezout. I heard Bezout before. I don't know. Whatever. I'm not French. This existence of numbers, that linear combination of the numbers times the relatively prime numbers give you back 1, and how that generalizes to polynomials, I think it's very, very interesting. But then again, the fact that prime polynomials behave like prime numbers is also very intriguing, isn't it? Anyway, our next topic, of course, is diagonable, which I usually say diagonalizable. So we'll talk about that next. I'm going to start it and stop it here again.